or A minus. Bloody hell. It's like a honeymoon course. Right. This is not honeymoon, this is doom, 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 doom. We all die. Right. Okay. So we have to determine the spacing. And you know, with a problem like this, initially it looks really, really complicated, but it's not. Okay. This is where failure analysis comes in. Okay. But the first thing we do, can you tell me where failure will occur? At the joints. And on that screen, the joint has how many sections? How many failure you see? 3. Well done. So failure will occur here. You see that? Here. Where's one more? And here. All right. Failure will occur at that 3 region. Okay. So now, it's good that we learn about what? Shear flow distribution. Okay. So now, if we're going to design the shear flow will look like this. What did I just draw? The major web what? Controls the what? The flow. And then when you know this will come in, this will come in, right? And then this will do this, right? So these are your terminus, and this is your what? Your terminal. Okay, so this is your terminal 1, terminal 2, terminal 3. Failure region 1, failure region 2, failure region what? 3. Okay, the fact that you know thin one analysis, okay, and you know how the shear flow distribute. Question for all of you: how to determine the spacing of the what? Of the horizontal nail. We know that the formula that we are going to apply is a very straight formula, very innocent like me, but not so innocent. This is the formula. Right? Resistance force divided by fastener spacing. This is the only what? Formula. Now, question for you. Let's consider the horizontal nail. Let's consider F1, failure region 1. What area do you consider? Yes. Left side rectangle, the small rectangle. Spot on. You only consider the shaded region. Are we clear? Now, some of you might ask me, Eugene, why don't I consider F2? Yes or no? Why don't we consider F2? Because the terminal 1 and the terminal 2, are they connected? They are not connected at all. Are we clear? So for this case, you only need to consider the what? That shaded region. Okay. So for this case, I don't have a lot of information we have to do from ground zero. Okay, so let's do from ground zero. So we have to find our, I'm just going to find our I, okay. So we are going to have section. You know what? I'm going to just take from the solution manual. I don't waste your time. So bear with me. Okay. You're not supposed to see. It's kind of private. Solution manual is like the prof being naked. Okay. So give me like 1 second, okay? So 7.46 or 7.47. So the wait. 7.47. Give me a minute, okay? Not or less than that. Okay. So the I is equal to 337.43. The I is equal to 337.43. So the I is equal to 337.43 inches to the power of 4. And the Y bar, let me see the Y bar. The Y bar is 3.3548. Okay, so 3.3548 inches. Okay, right. Coming back to here. So what we have just discovered, is it back on the board? Oh shit, it's dead. Oh, did it come back? Okay. So what we have is I is 337.43, Y bar is 3.548. And this is from the what? From the top. So it is this section that we only need to consider. So the Q Z, so this is equal to width, depth, and Y bar. So the width is equal to 1. The depth is equal to 3. The Y bar is equal to 3.3548 multiplied by, or not multiplied, seriously, Eugene, minus by what? 3/2. So this will be equal to 3.3548 minus by 3/2 times by 3 times 1 is equal to 5.5644 inches cubed. Let me do it again. 3.3548 minus by 3/2 times 3 times 1, 5.5644. Okay, so once we get that, so Q is equal to, so the V is equal to 700. The Q is 5.5644. The I is equal to 337. And then the resistance force is given to us to be 100. And this is divided by the spacing. And we know that this will be multiplied by 1 because I put 1 over there because this is a single what? Single shear configuration. So therefore, the spacing will be equal to 100 then divide by 700 divide by 5.5644. So this is equal to 100 times 1 times 337.43 divided by 700 divided by 5.5644 is equal to 8.66 inches. Okay. So now next thing is we want to calculate the vertical nail. So the vertical nail, we are going to look at F3. Okay. So F3 is over here. So we know that the first moment of area cannot cross the centroid whatsoever. So the region to consider for F3 is now you have to consider this entire region. Are we clear? Makes sense? Now, some of you, now, why don't we consider the web? The major web? Because failure will occur before the what? Before it hits the what? The major web. Are we clear? Right? That's why you take it up to there and up to there only. Make sense? Okay. So from here, we are going to find the first moment of area. Again, once you know where the position of first moment of area, Bob's your uncle. Yes or no? Don't ask me why it's Bob, okay? But Bob's your uncle. Means you got it done. So now, or in France, Pierre is your uncle, whatever, okay? I'm just making that up, okay? Monsieur, okay? So now, we are going to find the first moment of area of this entire section now. Now we have to consider the left web or the minor web, okay? We take the whole thing. Is it logical or no? Right? Right? Nothing unexpected. Am I right or wrong? Okay. So now we are going to calculate the QZ. So we know that this is twice 5.5644. Now, why the twice of 5644 is from here? Okay, so these are for the what? For the minor web, for the small web. Okay, then plus the width is 10, the depth is 1, and then you have 3.3548 minus by 1 over 2. Okay, so this will be equal to 2 times by 5.5644, 1288. Let me do it again. 2 times by 5.5644 plus by 3.3548 minus by 1 over 2 times by 1 times 10, 28.548. Let me do it again. 3.3548 minus by half times by 10 times 1, 28. Okay, so this will be equal to 11.1288 plus by 28.548. So it's equal to 39.6768 inches cubed. Okay, so again, we go for Q is equal to 700 multiplied by 39.6768. And then we're going to divide this by 337.43. Okay, that is our I space 100 multiplied by 1 because of single shear. And then this is our what? Spacing. So our spacing will become what? 100 multiplied by 1 multiplied by 337.43. And then we're going to divide by 700 and then 39.6768. Okay. So 100 times 1 times 337.43 divided by 700 divided by 39.6768. 1.215. And it makes sense, right? The spacing has to be what? Closer. Why the spacing have to be closer? Because we have a much larger what? First moment of area. Okay. Now, let me pick another problem that will tease your mind. Okay. I hope you are challenged. Okay, so let's look at another problem. Once you have seen enough problem, this is really easy. Okay. To solve all this problem, one of the best solution is you have to speak to yourself. Okay. Now this is not a straightforward problem, but I'm going to do it. Okay. I'm not saying that I love this question, but this question we can break one of the rules. Okay. So this is the question now. Okay. The beam is constructed from 3 boarded bolts together as shown. Determine the shear stress, the shear force developed in each bolt if the both are spaced S is equal to 250 millimeters apart, and the applied shear force is 35 times 10 to the power 3. Okay. So for this case, I want to declare that I don't spend time looking for it, but the Y bar, the centroid is 186 or 0.18676 meters, and the IZZ is equal to 0.270236. 0.270236. Bloody hell. Times 10 to the power minus 3 meter 4. Okay, so these two are given. Now, if you were to look at where 0.1867 or 0.18676 is, okay, it is going to be somewhere around here. So the height from here to here is equal to 0.181676. Can someone tell me what is so unique about this problem compared to what you've seen before? Yes. Hey? Yep, it's not symmetrical, but what else? I want you to focus on the bolt. Yes. Yeah. The centroid, well done. The centroid is above the what? Above the bolt. Again, I'll write down. The centroid is above the bolt. Right? So now it's confusing. Right? Now it get confusing. But the rule still stands. Okay, one rule still stands. One rule can be broken. What is the rule that can still stand? The member must distribute the